Welcome to Maths with EJD. In this video, I'll be talking about power method for finding a dominant eigenvalue. In the previous video, I started talking about eigenvalues and eigenvectors from the angle of numerical analysis because I've talked about eigenvalues and eigenvectors extensively under the matrices playlist, the very first playlist in this on this channel. So let's see power method for finding dominant eigenvalues and what they hold for us. What that holds for us actually. So the power method is an iterative numerical technique used to approximate the dominant eigenvalue The dominant eigenvalue is actually the eigenvalue with the largest absolute value. And its corresponding eigenvector for a square matrix A. It is useful when analytical solutions are impractical for large matrices. Okay, so let's talk about the algorithm for this. Okay, the first thing is you choose an initial vector, x naught. So that x naught should be non-zero, right? It should be non-zero. And it is typically with all ones, typically with all ones. Of course, it can be without ones, but it shouldn't be zeros. That's all that really matters. Then the second thing is that you can compute xk plus 1 equals axk. Xk plus 1 equals axk, like this. Then step 3, you normalize xk plus 1 to prevent numerical overflow. Normalize xk plus 1 to prevent numerical overflow. Then the fourth point is to approximate the dominant eigenvalue using lambda k, which is approximately xk transpose, then xk plus 1 that you would have computed up there. Then you normalize with xk transpose xk like this. Okay, so that's the algorithm for this. Let's take a practical example of this. Example, given A, which is 4, 1, 2, 3. Okay, so just like we said, the first step 1, given this, right, the first thing you want to do is initialize x naught. Take that to be 1, 1 like this. So as far as it's non-zeros. So it can even be 1, 0, or 0, 1 or anything, but any arbitrary matrix, any arbitrary vector that is not zeros, right? So initialize x naught. So if you do that, then the next thing you want to do is to compute. So next, you compute x1, which is a x naught. Okay. Now you have your a to be 4, 1, 2, 3, and x naught is 1, 1, just like what we have up there. So that means that x1 is equal to, so to do this now, uh just like so this is a 2 by 1, this is a 2 by 2 matrix, and this is a 2 by 1 matrix. So it means they are going to write this twice, this 1, 1, 1, 1, and then for this now, this is, I mean, you're writing it twice because this has two rows, right? So this is 4, 1. So the 4, 1 comes over here, like that. Then this is 2, 3. So the 2, 3 comes here. Then you can then cover it up. So you have x1 now to be equal to 1 times 4 is 4, 1 times 1 is 1, 4 plus 1 is 5, 1 times 2 is 2, 1 times 3 is 3, 2 plus 3 is also 5. So your x1 is 5, 5. So that's that. The next thing is so we are talking about the iterations now, right? Um okay, let's talk about first. This is actually the first iteration. First iteration. Okay, so we have x1. So we now need to get lambda 1. Lambda 1 now is approximately, from the expression we have up here, lambda 1 is actually x. What should I call this? I think we should actually have it as lambda 1, of course. So it's better to call it lambda k plus 1. It's better to call this lambda k plus 1. It makes more sense to call it lambda k plus 1, okay? So that will now be, so lambda 1 is now approximately x not transpose x1, okay? Because normally we expect, okay, let me just write the full thing so we get the gist. Okay, okay, I have to leave this the way it's this lambda k plus 1, right? I think it's better to have it that way for easier reference. So what we have said is that lambda k plus 1 is approximately x k transpose xk plus 1 divided by xk transpose xk. So that means that lambda 1 would be approximately x naught transpose, then x1, that's taking it like k is 0, and this is all over x naught transpose x naught. So this makes more sense like this. So what we are basically doing here is to say that um so that lambda 1 now is approximately x naught transpose is, x naught itself is 1, 1, this 1, 1. So the transpose will now be, it's a column vector, so the transpose will be a row vector this way, 1, 1. Then x1, we already have x1 to be 5, 5. So it's the row column vector 5, 5. Okay, this is 5, 5. Then all over, then x naught, this 1, 1, then 1, 1 this way. Okay, so that means that lambda 1 is approximately, so this is just we write 5 once. So because this is 2 by 1 by 1 by 2 by 2 by 1, it's going to give us about 1 by 1 matrix. So we have 5, 5, 1, 1 like this, divided by 1, 1, 1, 1 again. So this means we have lambda 1 to be 5 times 5, 5. So this is like 5 plus 5 divided by 1 plus 1. So lambda 1 is equal to 10 over 2. So, I mean, that's approximate, that like we've been saying, right? So lambda 1 is actually equal to 5. So that's our lambda 1. So that's first iteration. So for second iteration, we go again. Second iteration. Okay. Now, the iteration starts with x, right? So that's x1. So we go for x2. So x2 now is equal to ax now ax1, right? Ax1. So that means x2 is equal to 4, 1, 2, 3, right? Into x1 is 5, 5, if I still remember that correctly. Let's check. A is 4, 1, 2, 3. Then x1 is 5, 5, okay? So we have x2 now to be equal to, so because we have two rows here, so we have 5, 5 and 5, 5. Then invert 4 over 1. I mean 4, 1. So this 4, 1, and this is 2, 3. So now x2 is equal to 5 times 4 is 20. 20 plus 5, that's 25. I mean, for this, yeah, that's 25 in short. And then 5 times 2 is 10. 5 times 3 is 15, another 25. So we have this, okay. Um, okay, so that's x2. So we now need to go for lambda 2 again. So we go for lambda 2. Now, lambda 2 is approximately lambda 1 transpose. No, x1 transpose actually, x1 transpose x2 all over x1 transpose x, something like this. X1 transpose x1. So lambda 2 is equal to, now x1, what is x1 again? X1 is 5, 5. So x1 transpose the row vector, the column vector becomes a row vector. So we have 5, 5 like this. Then x2, that's what we just got now, which is 25, 25 divided by 5, 5, then 5, 5, like this. So lambda 2 now is equal to 25, 25 multiplied by 5, 5 divided by 5, 5 multiplied by 5, 5. Okay, so well, we can have it together like this. Okay, if you like. So lambda 2 now is equal to 25 times 25. 25 times 5 is 125. 125 plus 1. So it's more like 125 plus 125 divided by 25 plus 25. So lambda 2 is approximately 250 divided by 50. And again, lambda 2 is equal to 5. Okay, is approximately 5. So interestingly, that is still being maintained. So let's go one more iteration before we bring it to a close. So um, now we have third iteration. So since it's always already giving us 5 all the way, we can already imagine that the gap between that one and this one is the same. So we don't have to keep wasting time. But let me just do one more for the fun of it, because we keep getting 5. So it means the dominant eigenvalue is most likely 5. 5. So of course I know the eigenvalue of this, so I'm going to say it at the end of the day to actually show what we mean by dominant eigenvalue more clearly. So now we have all that, right? So we go for the next one. Of course, this case is easy. Third iteration, we go for A3, right? So we have A3, no, X3. So again, X3 is equal to AX2. So X3 now is equal to A, which is 4, 1, 2, 3. I mean, 4, 1, 2, 3, sure. 4, 1, 2, 3 multiplied by X2. Now our X2 is 25, 25, right? The numbers are getting big now. 25, 25. Okay. So X3 is equal to, again, 25, 25, then 4, 1, 25, 25, 2, 3. So that's X3. So X3 now is equal to 25 times 4 is 100. This is 125 up here. Down here, 25 times 2 is 50. 25 times 3 is 125. So 125 times 50. I think that's 175, right? 175. Yep, 175. So that is X3. So we can now get lambda 3. Lambda 3 now is approximately, or should I go black? Okay, lambda 3 is approximately x2 transpose, then x3 divided by x2 transpose x2. That's the normalization happening right there. So lambda 3 is approximately, what is x2 again? If you remember what x2 is, x2 is 25, 25. Okay, so that's so that means we have 25, that is 25, 25 into X3 is 125, 175, 125, 175. That's a very big number. We don't have to come this far actually because we already see that the eigenvalue is most likely 5 because we've got that twice. Normally, if we do the error, the what is it called now? Convergence criteria, you see that the difference between the second one and the third one is just 0. So we don't worry ourselves. So this is now 25, 25. Okay. So it's more like we're just doing a lot of stress. But let's go. So lambda 3, we are here. So let's just do it. Okay. What can I do now? What can I do? What can I do? So this is 125 times 3, right? Um, okay. So this is 125, 175 multiplied by 25, 25. This is totally not necessary, like I said. 25, 25, 25, 25. So this is like we have lambda 3 equals, so this is 125 times 25. That's 25 raised to power. Okay, so that's I think I need to punch a calculator. Okay, I can go for that for sure. So this is now 125 times 25, 125 times 25. That's 3125. So we have 3125 plus 175 times 25, 175 times 25. That is 4375 all over 25 times 25. That should be 625, I think. 25 times 25. That is 625 plus 625. So lambda 3 is approximately 3125, 3125 plus 4375, 4375. That is 7500 all over 625, 625, 625, 625 plus 625. That is 1250, 1250. So 7500 divided by 1250. So that's simply 5. Oh, is it 5 or 6? 75 divided by 1250. So that's 6. Okay, I think it's already diverging. Let's see. 125 times 25. 125 times 25. 3125. 175 times 25. 6125. 6125. 125 times 25. 3125 plus 175 times 25. 7500. Okay. Divided by 25 times 25 plus 25 times 25. That's 1250. Yeah, I mean, this is like 6, which is, this is 7500 divided by 1250. I mean, so we are moving away from what the answer should really be, but it's fine. So this is now giving us approximately 6, which is, I mean, already far. So we don't have to come all this way, right? Now, at this point where we know we have got, as at this point, right, we have got what the answer should really be. So around here, right, we have got what the answer should really be. So we can even conclude that the dominant, the dominant eigenvalue, dominant eigenvalue is 5. So, but we can get the eigenvector too, right? To get the eigenvector, just go to the next step. This thing we computed here, this can give us the dominant eigenvector. Uh, okay, I mean, it's giving us roughly 1, 1, right? So if you look at this, right, we can say this is like, so if this is you can say this is 125 over 175, then 175 over 175. Okay. So that's approximately, of course, the other one down there is 1, right? 125 over 175 is also very close to 1. So 125, 125 over 175, that's also close to 1. So this is like 0.7 to 1. Okay. So we can say so we see that the dominant eigenvalue is 5, and the dominant eigenvector corresponding to the dominant eigenvector 0.71. But actually for this matrix, right? For matrix for A equals 4, 1, 2, 3 normally, right? The dominant eigenvector, the biggest eigenvector. So we can say absolute value of lambda max would actually be is actually 5, and the dominant eigenvalue, if we can call that Vmax, is actually 1, 1. Okay, so that works. So that's how to do the power method. But I mean, in this case, we actually can compute the eigenvalue and eigenvector, directly. But I mean, we demonstrated it using this one so that we can actually see how this works. So in case you have a matrix whose eigenvalue is difficult to compute, this is the way to go about it. So bye. If you have not subscribed, please go ahead and do that. Subscribe and hit the notification bell so you can always get alerted each time a new video is released. Then comment, let me know how helpful this video is for you. And of course, let me know if there's a topic you'd like me to teach or a question you'd like me to solve. Then like and share so that more people can have access to this video. Bye.